Our tool EMILE-UI is an interactive tool for explanation evaluation. This is the simple interface built based on Streamlit. In the left panel, you can choose the input data, such as model architecture, model weight, explanation method, and other hyperparameters. On the right side, we see the visualization. At the top of the right panel, it will show the image's class prediction for the test image and the perturbation curves below. We will talk about that later. At the bottom of the panel, we will see the input image, saliency map, and perturbed images with the predicted classes. Let me upload the test image from my computer. Currently, it supports only JPEG image format. Then, I upload the ground truth label file. In this demo, we use a CPU and a small image 32 by 32. This image is from the CIFAR10 test data. Secondly, we select the neural network architecture. We also input the number of classes. Then we upload the weight of the neural network. We also choose noisy linear imputation to remove the features from the image. And we use the integrated gradient (IG) feature attribution method for saliency map generation. We wait a few seconds for the result. The model's prediction is the automobile, which is correct. Now we look at the detailed description of our interactive system, and below, we see the perturbation curve. Here we see the input image, saliency map, and two perturbed images generated by removing 10% of the most and least important features. 10% feature removal does not affect the model performance. We see it form the morph and lerf curves. The morph curve is generated by removing the feature iteratively from the image, according to the saliency map, and lerf curve is generated by removing the least important feature from the image in an iterative manner. We see that the morph curve drops before the lerf curve, and this means that the saliency model output is consistent with the feature importance represented by the saliency map. At 10% feature removal, we see nothing changes in the input images on the right. Moreover, model predictions are still correct. Now let us increase the feature removal percentage. We see that model accuracy drops when 40% most relevant features are removed. So we decided to see what the model sees when we remove above 40% of features. Let's remove 59% of the features. The perturbed image generated by the most important feature removal has changed the image in different regions. Also, the prediction of the model change, while the image generated by removing 59% least important feature did not change at all. Also, the prediction on that image is also correct. From this interface, a user can see what the model sees when it changes its decision. We see that the image perturbed in morph order has a visible car, but the model sees it as a cat with a probability of 0.93. Now let us remove 92% of the features. We choose this because we see that it is higher than the percentage when the lerf curve changes the decision. We wait for few seconds to see the perturbed images. After removing 92% of the features from the image, we see that the car is not detectable by our eyes, and the model also does not see any cars there. However, our model still detects an airplane in both images, with a probability of 0.73 and 0.80, which are quite high probability values. Here we first observe a consistent saliency map, and our model behaved according to the saliency map, which can promote user trust in the attribution method. However, later we see that model is not robust in ignoring unknown objects with lower probability. This tool hints at how misleading our model could be in certain situations.